Hey everybody, coming to you live yet again. I'm here with Chegg, bringing you Organic Chemistry 1 office hours all semester. That's every Tuesday, 5 p.m. PST. Please check out the QR code on the top left if you want to see what other courses Chegg is covering. They're doing math and all kinds of different courses, so you can get help on all of your classes this semester. So, once again, we're covering Organic Chemistry 1 here today. If you are watching, you can feel free to ask me questions in the chat. Keep them Organic Chemistry 1 related as much as possible. They can be pertaining to the problems that I've prepared and I'm going over, or they can be unrelated. Honestly, any Organic Chemistry 1 question, I will be scanning the questions in the chat and we'll try to answer every single one of them if I can. So, yeah, let's go ahead and get started and take a look what we've got here. So first up, we've got this one here. Given the following NMR spectrum and empirical formula, propose a structure for the compound. So this is a little bit different, right? Usually we are given a structure and a spectrum, and we are asked to assign the protons in the compound to the peaks in the spectrum. So that's one type of NMR question that you could be expected to answer. There are a few other ones too, but this one is an interesting one where you're given an empirical formula, or actually, well, a molecular formula in this case, and asked to propose a structure. Right? We want to figure out what is the molecule that this spectrum represents. So we've got C4H9Br. Now that's a small enough molecule that a decent way to start might be to just go ahead and draw all the possible structures, right? What are the different structural isomers that have this molecular formula? And so let's see. So the best way to do this would be we know we have to have a 4-carbon skeleton. So how many ways can we arrange a 4-carbon skeleton, and how many ways can we place a bromine atom on that 4-carbon skeleton? So obviously we can have a straight chain, right? We can have a 4-carbon straight chain. Now, where can we put a bromine on the 4-carbon straight chain? We could put one on the end, or we could put one on one of the internal carbons. Right? So if we put it on either end, it would be the same. And if we put it on either internal carbon, it would be the same. It's either 1 bromopropane or 2 bromopropane. You can't have 3 bromopropane or 4 bromopropane. That's redundant. That's not, it would just be the same as one of the first two. So that's all we can do with straight chain. Wait, did I say, no, butane. I meant butane if I said propane. Sorry about that. So we've got 1 bromobutane, 2 bromobutane. We can also make the carbon skeleton isobutane. Okay, so if we make it isobutane, now where can we put the bromine? We can put the bromine on one of the methyls, on any of them, right? They're identical methyls, so we can put them anywhere. Or we can put it on the central carbon and have this the tertiary alkyl bromide. It's hard to do the dash bonds with these things. Okay, so these are the only possible structural isomers pertaining to the molecular formula that we've been given. So one of these has to match this NMR spectrum, okay? What it's going to be? Well, there's a few different ways that we could do this. We could acknowledge that that these different compounds would produce a different number of peaks. We can take a look, and then once again, obviously, we can look at splitting, integration, and chemical shift. So there's no right way to do this. So let's just start interacting with the data and see what it brings up. So, for example, we've got a doublet here, or actually, it appears to be a doublet. Maybe if we zoomed in, it would be a little bit different. But what can we say about this? It's integrated to 6, and it's relatively upfield. It's upfield, so it's the furthest away from the bromine, right? The protons that pertain to this resonance ought to be the furthest away from the bromine atom on the molecule. And now, when you have a peak integrated to 6, usually what that is 2 identical methyl groups. Not always, but often it is going to be 2 identical methyl groups, which indicates some symmetry for the molecule. So that's one bit of information. Honestly, with that alone, we probably could make the assignment, but let's just keep going here. Then we have a resonance that's integrated to 1, and it's highly it's a multiplet, right? It's split quite a bit. Okay, so that means that we have one proton that is being split by many other protons, right? We don't even have to count exactly how many, but this is split into at least 7 peaks. So probably 6, 7, 8, right? There's a lot of neighboring protons. So we have to have one proton that has a lot of neighboring protons. And then we have another peak that is integrated to 2. And this also appears to be a doublet, right? From this vantage point, it looks like a doublet. And it is the most downfield, which means it is probably the closest to or adjacent to the bromine atom. Okay, so so with that, we can now you can go either way, right? I chose to do it this way. What you also could have done was looked at the structures and made predictions about the spectrum that you would see based on those structures, right? And then you could just see which one matches your prediction. Or you can do it this way, right? It doesn't even matter. I didn't even decide which way I was going to do it until I was doing it, right? I just said, okay, let's look at the data. And so we're looking for 2 identical methyl groups probably that are upfield. And then we've got 1 proton split into a multiplet. And then we've got 2 protons split into a doublet that are right next to the bromine. So which structure matches that? Over here, this linear one, 1-bromobutane doesn't seem to work, right? Because we would have a resonance for these 2 protons, a resonance for these 2 protons, a resonance for these 2 protons, and a resonance for the 3 methyl protons. So we ought to see 4 peaks. And so none of the integration works. Certainly nothing is going to be integrated to 6. That doesn't make any sense. We're going to say we don't even have to look anymore. That's not gonna work. Okay, over here, this also would probably have 4 peaks, right? Because we would have the methyl protons would be the most these methyl and these methyl protons. So at first we might think, okay, we have 2 methyls, so we could have 6 identical methyl groups, but they're not identical, right? It's not symmetrical. If we had another carbon here, then the 2 terminal methyls would be identical, but it's not. The protons on this methyl are closer to the bromine than the ones out here. So they would offer 2 different resonances, and the one over here would be more downfield because it's closer to the bromine. So here, again, we're going to expect 4 peaks. We're going to expect one for the most upfield would be this methyl, and then somewhat tied would be one integrated to 2 and one integrated to 3 for the CH2 and the methyl there. And then the most downfield would be one integrated to 1, and that would be heavily split. It would be split into a multiplet. But we don't see 4 peaks. We see 3. So that doesn't really work here. So let's say no to that one. Now, how about this guy? Okay, so we've got 2 identical methyl groups, right? This carbon-carbon bond is constantly rotating, right? So those 2 methyls see the same chemical environment as this carbon-carbon sigma bond is spinning. So we do have 2 identical methyl groups that would be integrated to 6. Now, would they be a doublet? And yes, they would be a doublet because we have just this 1 proton on the adjacent carbon, right? So this 1 proton here is splitting the resonance associated with all 6 of these protons into a doublet. So that works. And this would be the most upfield, right? This would be the most upfield because it's farthest away from the bromine. So that checks out. This peak works. Now we've got the one in the middle. So we go a little bit closer to the bromine. We've got 1 proton, and it's heavily split into a multiplet. So that again works, right? Because we have this 1 proton. It's closer to the bromine, but not the closest. And it should be split. It's heavily split. It's split by these 3 protons, and the neighboring 2 protons over there. That's 8 protons next door. So the n+1 rule dictates it should be split into 9 smaller peaks. And we don't even have to count, right? It starts to get very small towards the edge and maybe difficult to discern, but it doesn't matter. It's a multiplet. We see that it is indeed very heavily split. That's good enough because the integration and the chemical shift also serve to corroborate this peak. So we've got that. That one looks good. Then lastly, we have integrated to 2. And so that would be these protons here, and oops. So these 2 protons here, and they will be the most downfield because they're immediately adjacent to the bromine. And it should be split into a doublet because they're only split by the one adjacent proton. So that also makes sense. So all of these data agree, right? All of these data agree. It is the chemical shift and the splitting and the integration for all three peaks agree with this structure. So there's just no way that it's not going to be this one, right? It's not like, this has some data and the other one has some data correct. It's going to be all or nothing, right? At least at this level here where we're approaching it with very easy, simple compounds. It should all agree. So that one's that. And then just to be thorough here, this guy would have only two peaks, right? All of these methyl groups would join together to make a 9H doublet, right? It's 9 protons, so it would be integrated to 9. Very, very, very tall peak. And no, sorry, I was totally wrong. That would be a singlet, actually. 9 protons, and that would be a singlet because there is no hydrogen on that central carbon, right? There's a bromine there, no proton. So it would be, that's it, right? You would only have one peak. So if we had a spectrum that was one peak, we would take a glance at these options and know immediately, oh, it's got to be that one, right? We have 9 chemically equivalent protons generating one 9H singlet. That's a dramatically different spectrum than any of these other possibilities. So that can be ruled out pretty easily. So this one's not right. So this is a really good one. I like ones like this that force you to use critical thinking, right? The first thing you had to do, now you didn't have to do this, right? I went and exhaustively drew out all 4 possible structural isomers that pertain to this molecular formula. You don't have to do that, right? One thing that you could do is just start piecing together fragments like a puzzle. You might look at this and see, okay, we got this integrated to 6. I think I have 2 identical methyl groups. All right, here's my methyl groups. Okay, they're going to be connected by a carbon in the middle. Then what happens? And then you can start building the molecule from there. That's it. Any way you want to approach this is fine, as long as what you arrive at, the data has to match, right? All of these, the chemical shift and the integration and the splitting patterns for these 3 resonances have to match the structure flawlessly. So I chose to draw all 4, and then we went and made predictions and then matched the peaks. And then we were very confident that that was the structure there. So that's that isobutane with the bromine on the methyl, and that's going to be that one. Okay, let's take a look and if I missed any questions here. Feynman's technique of integration. I'm not really sure what that is. It sounds like it could be math, but if it pertains to NMR, it sounds like it would just be a way of calculating the area under the resonances, which honestly, in this day and age, we don't have to do that, right? You take a sample and then the program in the computer, right? You highlight a peak and it automatically it goes by the number of pixels under the peak and it tells you the relative integration. Actually, what you do is you take the smallest peak and you highlight that and assign it the integration of 1, and then it calculates all the other integrations relative to that one that you assigned. And so it's not absolute integration, but it'll tell you, all right, if you're saying that's 1 proton, then this has to be 6, this has to be 2, etc. So we really don't calculate anything with the integration these days. Oh, okay. Draw the line structure of, okay, R133. Try. Okay. All right. Yeah, we can do that. Okay, I'll do it right here first before we do number 2. So we have a cyclopentane. And we have pentanol. So we have 1 all. So we'll call that there. And then we also have 1,3,3 dimethyl. Okay, so we have that. And let's hope that I did the stereochemistry right. Otherwise, I'll switch it. Let me just double check. So 1,3,3 trimethyl cyclopentane 1-all. Okay, yeah. So we've got 1 and 1,3,3. Okay, so I think that I did do it properly. So so the answer is either this or the OH and the methyl flipped on there. Let's just make sure I'm correct. So there's this is the only stereocenter, right? There's one stereocenter here. So well, okay, going back to the beginning, just it's a cyclopentane. So we know we have a 5-membered ring, and then 1-all means that we have a hydroxyl on carbon 1. And then we have 1,3,3 trimethyl. And so on this same carbon, we have a methyl. And then on carbon 3, we have 2 methyls. So one on the dash, one on the wedge. And we're making sure that this is our stereochemistry. So what are the priorities here? Number 1 is certainly going to be the oxygen, right? And then the other 3 are tied. We have carbon, carbon, carbon. Carbons all tie. So we have to go to the next step after that. So this one is attached to hydrogen, hydrogen, hydrogen. So that's definitely going to be number 4. This one is attached to carbon, hydrogen, hydrogen. So I'm going to assume that's number 3. Oh, well, actually, this one is also bonded to carbon, hydrogen, hydrogen. But if we go again, this is bonded to carbon, hydrogen, hydrogen. This is bonded to carbon, carbon, carbon. So that's a little confusing, but remember with the Kahn-Ingold pre-log convention, we're going one atom at a time, okay? So oxygen wins without a question, but then carbon, 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 these 3 are identical carbon atoms, so we have to see what they're connected to. This carbon is attached to hydrogen, hydrogen, hydrogen. This carbon is attached to carbon, right, this next carbon, and then the 2 implied hydrogens. This carbon is connected to this carbon and the 2 implied hydrogens. So we know from that we've assigned 4 for this, but these 2 are still ambiguous. So we have to keep going. So now we go further, right? And now we say this carbon is attached to this carbon and then the 2 implied hydrogens. And then this carbon is attached to carbon, carbon, carbon. So we had to go 2 points of difference away to figure out that this direction is priority 2. Because carbon, carbon, carbon beats carbon, hydrogen, hydrogen, right? And carbon, hydrogen, hydrogen beats hydrogen, hydrogen, hydrogen. So we've made our assignments there. And so luckily the lowest priority group is facing away from us. Priority 4 is that methyl, so it is facing away. And so we are already in the privileged position to assign RNS. And so with the lowest priority group away, we trace from 1 to 2 to 3. And we're going around clockwise. So that is R. So we were right. If it ended up being that as drawn, it was S, and the question said we have to draw it R, we would just flip that stereocenter, right? We would just flip the hydroxyl and the methyl. When you invert any when you swap any 2 groups on a stereocenter, you invert the chirality of that stereocenter. So take any 2 groups. If it's R, if you swap 2 groups, you get S, no matter which 2 groups they are. So yeah, I hope that helped. Okay. Nassim says, wait, so a doublet means 2 H friends next to him. So no, a doublet would mean that there is 1 neighboring proton, right? Because of the n+1 rule. So like, for example, on the compound that it was, this resonance integrated to 6 is split into a doublet because there is 1 neighboring proton. So you have 1 neighboring proton, n equals 1, and then n+1 is therefore 2. So the resonance is split into 2 smaller peaks. So 1 neighboring proton splits it into a doublet. 2 neighboring protons splits it into a triplet. 3 neighboring protons splits it into a quartet, and so forth. Okay, seems like you asked that there. Hope that helps. Poninka asks, can there be multiple valid solutions? If you met the NMR one, no. That this is the only structural isomer pertaining to this molecular formula that matches this NMR spectrum. There's no other answer. Maybe you meant this, but that too, there would not be any other valid solution there. You Can Soup Chicken says, the concept of catalysts is so bizarre to me. How can something be part of a reaction and have no change? So it's not that a catalyst does not undergo change; it's that it just returns to its original form once. So, like if like aluminum trichloride promotes a Friedel-Crafts alkylation reaction, it interacts with the chloroalkane. The chlorine attacks the aluminum. It forms this larger complex. But then at the end of the reaction, that fragment leaves and aluminum trichloride is returned to its original status. So a catalyst will interact with the substrate, promote some reaction, right? It'll lower the activation energy of a particular pathway, but then it is restored to its original form once the reaction is complete, which allows it to then go and promote another reaction and another and another and another and another. So a catalyst does interact often in covalent fashion with the substrate. It's just not consumed in the reaction, right? It's not used up. It's not used up stoichiometrically in the reaction. So Ram to the Future says, if we had an alcohol, would the peaks be further downfield because of the electronegativity, or is there something else that causes it to shift more? Very good question. Yes, I'm pretty sure that if this had been a hydroxyl instead of a bromo group, these peaks would be further downfield, because an oxygen atom is more deshielding than a bromine atom because it is more electronegative. Oxygen is more electronegative than bromine, so the deshielding effect would be greater, which would cause the chemical shifts of these resonances to be further downfield. Very good question. I believe that would be the case. Jofi says, why does a nitro group located on the meta position act differently than the nitro group being on the ortho and pair positions? So I'm not sure what you mean. That's ambiguous. Meta to what, or ortho and para to what? So a nitro group is going to be a meta director no matter what. There could be other substituents on the molecule also that have their own directing abilities, their own directing behavior that may compete with the nitro group, but the nitro group will always be a meta director. Okay, a lot of comments here. Very cool. Injecting AlCl3, just don't do it. Dave, how do you name a carboxylic acid as an alkene group based on IUPAC nomenclature? 4-chloro-2-meth. So not methoxy, right? Methoxy, an alkoxy group is part of an ester, not a carboxylic acid, right? So it would be, so take out the methoxy that you have there. It would be something, the rest of it works, right? 4N, right? 4-ene, that part is indicating where the double bond is, but you don't need one oic acid because that's implied, right? With a carboxylic acid, the carbon that bears the carboxyl is implied to be carbon 1, where we already know that by the IUPAC rules of carboxylic acids. So you have to indicate the position of the pi bond, but you do not have to indicate the position of the carboxyl group that will be carbon 1 for sure. Okay, let's get back to this. Okay, let me erase this because I wanted to do a question here. So, okay, which reaction mechanism could be represented by the following energy diagram? SN1, SN2, E2, none of the above. So, let's look at this. Let's look at this here. So X is the reactant. Y is, what do we call that? That is an intermediate. And Z is the product. And then we have transition state 1 and we have transition state 2. So the transition states are the highest energy moments, so to speak. They're the highest part of the hill that if you achieve that transition state, it will proceed to the next intermediate or product. And so then we have right here, this is delta H. Or actually, if this is potential energy, well, it could be delta H or delta G, right? Depends if we're displaying enthalpy or Gibbs free energy. So it depends. Could be either. And then right here, we have activation energy 1. And then starting from the intermediate to transition state 2, we have activation energy 2. Okay. So we clearly have a two-step reaction, right? Because of that intermediate, we know that we have one reaction that yields that intermediate, which will exist for some discrete amount of time, and then a separate second reaction will happen to give the product. So intermediates are species that exist for some amount of time. Transition states cannot be isolated, right? Transition states are achieved instantaneously, where there's an infinitesimal instant in which a transition state exists along the way to becoming the next species, the intermediate or the product, right? But an intermediate is formed and then will sit there. It will float around in solution until it reacts with something else. So we clearly have two steps here, X to Y and then Y to Z. So which of these, right, how many steps do we have for these? So SN1 is 2 steps, right? But SN2 is 1 step and E2 is 1 step. So those don't work. So clearly this is going to be SN1, right? Because SN1, the way that works is, okay, so we have, let's say we have this here. And what's going to happen first is the leaving group's going to leave, right? And that gives us our carbocation intermediate. And so that's going to be the rate determining step. That's the one with the very large activation energy because we're producing an unstable intermediate. A carbocation is an unstable species, right? The electron deficiency makes it unstable. And then some nucleophile coordinates, and that is going to be very fast, right? That's a quick one. Because this is stabilizing, right? We're neutralizing a carbocation, right? We're neutralizing the carbocation. So there's a very low activation energy, right? This is not an energetically unfavorable step. It's going to be very easy to get to that transition state where the nucleophile is coordinating to the carbocation. The very slight hill is just about the steric hindrance associated with the negatively charged nucleophile approaching that electron density on the neighboring alkyl. But it's a very low activation energy because it's a negative charge coordinate. Well, it could be a neutral, it could be a lone pair, but let's say it's a formally negative, let's say it's an anion. We have a negative charge approaching a positive charge. That's going to release a lot of energy when that bond forms, right? So this is very exothermic. It's very exergonic. So exothermic is negative delta H. Exergonic is a negative delta G. Either way, we're releasing energy upon forming this bond. So that's going to release a lot here. Very small activation energy. And so SN1 is the only one that works here. SN2 and E2 are all concerted reactions. They just happen like that, right? You have some substrate, and as the nucleophile is approaching, the leaving group is leaving. So as the bond between the nucleophile and the substrate is materializing, the bond between the substrate and the leaving group is dematerializing to the point where you have a transition state that's trigonal bipyramidal, where we have almost half a sigma bond between a planar substrate and each of the two, the one coming in, the one going out. So it's all concerted, happens all at once. It's not piecemeal. It's not stepwise. So this must be for the SN1 reaction. It also could have been an E1 reaction, which is why I didn't give that as one of the options. Then it would have been ambiguous. So that is something about energy diagrams. Remember, with any energy diagram, we're identifying reactants, we're identifying products, we're identifying intermediates, if any. If it's a one-step reaction, it'll just be one little hill. And then we are identifying transition states, and the transition states tell us what the activation energies are, right? The activation energy is always from the reactant to the transition state. So this first step had a very big one because that's the unfavorable, that's the rate determining step to yield the unstable carbocation intermediate. Second one has a very small activation energy because this is very favorable. We're going to the product there. So that's a little bit about energy diagrams. Very, very, very important in organic chemistry to understand how energy diagrams work, to be able to describe reaction mechanisms with energy diagrams, match steps in a mechanism to the pertinent energy diagram, that kind of stuff. You would definitely see a lot of questions pertaining to that. Okay. Laura says, can we do some acid and base pH chemistry review, Bronsted-Lowry? So that's really Gen Chem. Yeah, I mean, I'll just, pH is the negative log of the hydronium concentration. And so a lower pH means more acidic. So it's just taking something like, if the hydronium concentration is 10 to the negative 7 molar, taking the negative log of that just turns it into 7, which is just an easier number to work with. And so as the concentration gets higher, right, 10 to the negative 7 molar, 10 to the negative 6 molar, 10 to the negative 5 molar, that's increasing, right? The number on the exponent is going down, but it's a negative exponent. So as that decreases, the number is actually getting larger, right? 10 to the negative 2 is 0.01, 10 to the negative 1 is 0.1. And so it's just a way of communicating the concentration of hydronium in a solution. All right, more hydronium, more acidic, lower pH. That's all it is. And Bronsted-Lowry refers to proton donation, right? HCl is a Bronsted-Lowry acid because some base can go and take the proton. Right, so donating a proton, Bronsted-Lowry acid, accepting the proton, Bronsted-Lowry base. So that's it. Okay. Laura, so the Arrhenius definition is very outdated, right? Arrhenius defined it as just that which increases hydronium or hydroxide concentration, right? He said that, I'm pretty sure this is the case, but he said that an acid increases hydronium, a base increases hydroxide, which is actually very limiting because, number one, you're limiting yourself to aqueous solution. Right. If something is if something is an acid, if it can donate a proton, it should be able to donate a proton to other solvents, not just water. So Arrhenius is like a precursor to Bronsted-Lowry. So it's useful to know the definition of it, but it's not right. In organic chemistry, we deal with Bronsted-Lowry definition and Lewis definition. Usually Bronsted-Lowry definition. Usually when we're talking about acid-base chemistry, we're talking about the Bronsted-Lowry definition. We're talking about proton transfer. But we also use the Lewis definition because there are like Lewis acid catalysts that are not protic, like aluminum trichloride, where something can coordinate to the aluminum atom and it is acting as a Lewis acid. There's no proton though. So okay. Let's see. Yeah, Ryan just went ahead and pasted that in there. Okay, let's do the next one. Okay, so we have this alkyl bromide, and we achieved it with these reagents. So what did we start with? So what we need to understand is that this is going to promote anti-Markovnikov hydrohalogenation. So the peroxides are going to promote anti-Markovnikov regiochemistry. So we know that we did an addition reaction. So we have a substrate that must have a pi bond in it. But the question is, where was the pi bond to yield the bromine in this location? And so when we do an anti-Markovnikov addition reaction, the relevant group in question, in this case the bromine atom, goes to the less substituted carbon that was participating in the pi bond. So we know that the carbon bearing the bromine has to have been participating in the pi bond, but was the pi bond there or was the pi bond here? And the point is that if it was the one that if the bromine went to the less substituted carbon, that means that the pi bond must have been here, right? Because we have a primary carbon, a secondary carbon, a tertiary carbon. So with the pi bond here, the incoming bromine atom will go to the less substituted. That's the secondary. That's where we want, right? If we had put the pi bond on the terminus, on the end of the molecule, then the bromine would have had to go on the end, on the last carbon, on the terminal carbon. But that's not what happened, right? So we know the pi bond must have been here because between a secondary and tertiary carbon, the bromine going to the less substituted carbon would be the secondary carbon, which is where we want it. Okay. So we just have to know this means hydrohalogenation. So it's an addition reaction. We came from an alkene. And then the peroxides, the presence of hydrogen peroxide promotes anti-Markovnikov regiochemistry. And that will tell us where the pi bond must have been. Okay. Okay. Let's see. Abdullah says, why does giving an electron to another atom create a bond? That's not sure what you mean there. You can have an anion. You can have like a negatively charged nucleophile attacking a carbocation, and then the two electrons in that lone pair that are doing the attacking, one of them gets donated to the carbon, which neutralizes it. And in doing so, you form a covalent bond. That's the only thing I can think of that sounds like what you asked. Okay, let's try this one. So we're doing Diels-Alder, so the reason that's written there is because if it just said heat, it'd be a little bit ambiguous. But the point of a Diels-Alder is that there's no reagents other than the diene and the dienophile, right? You get the diene and the dienophile, you get a little bit of heat, and they'll snap together. So remember, Diels-Alder reactions always form six-membered rings. If you're doing Diels-Alder in the forward direction and your product doesn't have a six-membered ring in it, something went wrong. It's got to have a six-membered ring. Likewise, if we're doing retro Diels-Alder, if we're looking at a product and trying to figure out what the diene and the dienophile were to yield that Diels-Alder product, we have to undo the six-membered ring that was formed, right? And so with the six-membered ring, there's going to be a pi bond in there. Because remember, we're cyclizing. We've got three pi bonds. One pi bond remains a pi bond, but the other two become sigma bonds to close up to form that six-membered ring. So it's going to be these ones, right? We have to retrosynthetically cleave this bond and this bond, okay, and go backwards from there. So if we pull that apart, right, if we in our minds dematerialize these two sigma bonds and pull those fragments apart, what do we get? Well, we're going to get, whoops, how did that become a circle? We're going to get this diene, and we're going to get this dienophile. Okay, so the point is that when the product is a bicyclic structure, it means typically the case is that the diene was already cyclic. So this makes sense in the forward direction. If the diene is already cyclic and then it does Diels-Alder, we're forming a new six-membered ring, but this ring doesn't go anywhere, right? So this fifth carbon, right, if we want to go in the forward direction, right, this pi bond becomes this pi bond, the one that's in the product. This pi bond becomes this sigma bond. This pi bond becomes this sigma bond, right? But what about this carbon? This carbon is still there. This carbon is not participating in the cyclization, but it doesn't go anywhere. It's still got to be there on the product. So that's why we get a bicyclic structure on the product. So that explains the bicyclic product. Then these methyls on the product, those are still going to be there, or sorry, they were there on the diene, and because these were sp2 carbons, they're sp2 on the product, and they were sp2 on the diene. Those can be flat. We can put them flat in the plane. Those are not going to be wedges or dashes because these are sp2 carbons, trigonal planar. And then the last thing we have to understand is that on the dienophile, these methyls were cis on the product, and so they must be cis on the dienophile, right? So we would not draw this. This would not be the right, we don't want the trans dienophile because that's not what we got, right? When you have, right, the stereochemistry on the dienophile is conserved. You get, if you have a cis dienophile, you have the methyls or whatever groups they are, cis on the Diels-Alder product. So retro Diels-Alder, we're just identifying the six-membered ring, identifying the two sigma bonds that we have to retrosynthetically cleave, then pull the fragments apart, right? You pull them apart, what do you get? You get this, right? You get this fragment as the diene, and you get this fragment as the dienophile. So then you just draw them with the pi bonds shuffled the backwards way, right? So right, this one went here, this one went there. That gives us the diene, and then this one went here to make the pi bond on the dienophile. So that is that's your retro Diels-Alder. Nassim says, wouldn't addition of radicals always yield another radical unless it reacts with a halogen? So we're actually going to do, if we get to it today, I have the mechanism for anti-Markovnikov hydrohalogenation that we're going to go over. So to answer your question, yes, a propagation step, if a radical interacts with a covalent species, then you're always going to propagate a radical. You're going to get a new radical in a new covalent species. So that's what a propagation step is in a radical reaction. But the thing is that yeah. So if you not add, but if a radical reacts with a covalent species, you will get a new radical in a new covalent species. That's true. You can also have termination steps where two radicals react and give a covalent compound. OCL, I love Diels-Alder reactions. Yeah, I like them too. One of my favorites. Give says, wait, so when is it that you would begin to use wedges and dashes? Is it based on Vesper? And if so, how do you know when to bring them in? Okay, so yeah, so I do find that there's a lot of confusion at times. So like, for example, right, why are these methyls on wedges while these are not, right? And so the point here is that we have to understand the difference between an sp2 and an sp3 carbon, right? These guys are sp2, right? Those are sp2 carbons because there's a pi bond here, right? So there are no implied hydrogens on these carbons, right? This carbon has 4 bonds to other carbons. This methyl, this carbon, and then 2 bonds to this carbon. This carbon also has 4 bonds to other carbons. This methyl, this carbon, and the 2 bonds to that one. But these guys are sp3, right? These are sp3 carbons. There are implied hydrogens there. Right. So when you have an sp3 carbon, substituents have to be on dashes and wedges because that's right. sp3, right. sp3, like, okay, here's methane. Right. sp3 carbons, when you have a central atom that is bonded to 4 other groups, you're going to need 4 atomic orbitals to hybridize to make the sp3 hybrid atomic orbitals. And they're going to orient themselves in space in tetrahedral fashion, right? This is right. We've got 109.5 degree bond angles. That's the furthest away that four groups can be while all bound to the same central atom. And so that's different, right? With sp2, that's trigonal planar, that's flat. That's 120 degree bond angles, right? These are 120 degree bond angles because these carbons only have three electron domains. When you have three electron domains, carbon, 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 that makes a trigonal planar geometry, right? But when you go from three electron domains to four electron domains, right? So this carbon has methyl, carbon, carbon, implied hydrogen. So we definitely have to know where the implied hydrogens are because we don't draw them in on these structures. When we draw in line notation to save time, we don't draw all the hydrogens. So we have to know where the implied ones are. And so for an sp3 carbon like this, we have to go, okay, carbon, 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 implied hydrogen, four electron domains. This carbon here, methyl, carbon, carbon, implied hydrogen, four electron domains. Four electron domains, sp3 hybridized, tetrahedral geometry, 109.5 degree bond angles. That's when we got to use wedges and dashes. Okay. I hope that helps. Amir says, how do you differentiate SN1 and 2, E1 and 2? And if it is elimination, how do you know if it is Hoffman or Zaitsev? Okay, excellent question. So yeah, we went over this a lot in previous weeks, but we can totally take a look. So let's say SN1, SN2, E1, E2. So if we have a very strong base or nucleophile, if we have a very strong base or nucleophile, it's going to go ahead and do something, right? It's going to react with the substrate. It's going to push it around. It's going to replace a leaving group. It's going to grab a proton, do elimination. So we only see SN1 or E1 if it's a weak base or nucleophile, right? So that'd be something like, so strong would be like hydroxide, weak would be like water, right? So if it's very weak, it can't react with the substrate. It has to wait until the leaving group leaves, producing a very unstable carbocation intermediate. Then even the weak nucleophile can interact. Weak nucleophile, weak base, right? So that's the first thing probably that you look at. Strong base or nucleophile, we're going SN2 or E2. Weak base or nucleophile, we're going SN1 or E1. Then there's some other factors. Sterics, right? Steric. If the base is very sterically hindered, we would go elimination. Also temperature, right? Hot tends to favor elimination. Cold tends to favor substitution. That's because of the Gibbs free energy equation, right? We know that elimination is entropically favorable because you're going from two particles to three particles, two compounds to three compounds. And so the entropic favorability is magnified at higher temperatures. So higher temperature takes the entropic favorability, magnifies it, and makes delta G more likely to be negative, and therefore the reaction spontaneous. So check my previous live streams. The first 3 or 4 weeks, I focused a lot on SN1, SN2, E1, E2, because that's kind of the first stuff that you go, those are the first mechanisms you learn. And I talked a lot about this kind of stuff and predicting which mechanism would occur. So go ahead and check out my previous live streams on this. Okay. Give says, so as soon as hybridization enters sp2 sp range, it is no longer able to have implied hydrogens. No, I mean, it could have implied hydrogens still. So like, for example, here's a pi bond. There are implied hydrogens, right? Here's an implied hydrogen and here's an implied hydrogen, but there's only one implied hydrogen. So all of the carbon-carbon bonds are depicted, but carbon-hydrogen bonds are often not depicted. right? So all you have to do is count up the carbon-carbon bonds, and you know how many implied hydrogens there are. So for this carbon has 3 bonds to other carbons, right? 1, 2, 3. It's got to have 4 bonds, so that 4th bond must be to hydrogen. This carbon here is showing 1, 2, 3 bonds to other carbons. So there's got to be one there. This carbon is only showing 2 bonds to other carbons. So it's got to have 2 bonds to implied hydrogens. That one's sp3, right? Now we have wedges and dashes. Over here, this methyl, right? This one is showing 1 bond to other carbons. So we have to have 3 implied hydrogens, right? Same with this methyl group, implied hydrogen, implied hydrogen, implied hydrogen. So sp and also sp hybridized can also have implied hydrogens, right? Here's the implied hydrogen, right? We're not showing that terminal proton, but it is there. Sometimes it's drawn in, but you don't have to. So the point is carbon-carbon bonds are always depicted. Carbon-hydrogen bonds are typically not depicted. So you have to count up the carbon-carbon bonds that are shown, and however many are missing to get to 4 bonds for carbon. Carbon's almost always going to have 4 bonds unless there's a formal charge present. If it's a neutral carbon, it's got to have 4 bonds. So any missing bonds have to be to implied hydrogens. Okay, I hope that helps. Yeah, Caitlin says it's like you're supposed to immediately know whether to put something on a wedge or dash. So it's got to go on a wedge or dash if it's an sp3 hybridized carbon. So like, for example, what I just did here, right? This carbon, right, before I drew in those hydrogens, we saw that there were 2 bonds to other carbons. So to get those other 2 bonds, we have to have bonds to implied hydrogens, right? And so that means that it's sp3 hybridized. And so it's got to be tetrahedral. So one is going to go on the wedge, one's going to go on the dash. That's got to be it. Caitlin says, how do you reconcile a compound that is trans using syn addition, just imagining it in 3D? Not sure I understand here. Let me just erase some stuff. So I think what you mean is if we have a trans alkene and we're going to do syn addition, let's just say it's AB. We don't care what it is, right? So that's fine, right? We can do this. Right? So the alkene is flat, right? And so if A and B are adding to the same side, right? Syn addition means that the 2 groups, are adding to the same side of the molecule. So that means that they'll be on the same side of the product, right? So this is less confusing on a cyclic substrate where sigma bonds can't fully rotate. But as long as we do this, right, we can see they're both on the wedge or both on the dash, right? Could be the other way. But clearly, if they're on the same side of the product, then they were added to the same side of the alkene, right? Okay, cool. We caught up. Yeah, we got time for 1 or 2 more really quick. Okay, so let's do this organocuprate one. So I haven't mentioned organocuprates yet. Not all Organic Chemistry 1 courses get into organocuprates, but some do. So let's just it depends on the professor if they like to use these or not. So we've got this alkyl bromide and we've got an organocuprate. So what is this, right? We've got 2 ethyl groups. We've got a copper atom. We've got a lithium atom. What is this? What's going on? So we got to understand what an organocuprate is. We've got the 2 ethyl groups that are bound to the copper atom. The copper atom has a formal negative charge, and then the lithium cation is the counter ion that coordinates to the copper. And so what these are, organocuprates are sources of nucleophilic carbon, nucleophilic alkyl groups, right? Because what happens is if one of these alkyl groups leaves with the electrons in the carbon-copper bond, then copper will lose an electron and it'll be neutralized. Right. So we've basically got an alkyl anion. We've got a carbanion nucleophile. And then this is just like an SN2 substrate, like a normal one that we would normally see. So this is what we need, right? One of these alkyl groups is going to be the nucleophile. And we're going to go boom, boom, right? Now notice that, right, my arrow started in the middle of this bond. Right. And what this signifies is that this carbon is leaving with the electrons in this carbon copper bond. It's taking those electrons, right? And so that's why carbon is losing that's why copper is losing an electron, which is favorable because then it neutralizes. So this ethyl carbanion nucleophile is going to attack this carbon, just do a regular SN2, kick off the bromine, and we're going to get, so here's the product. Here is the carbon that was attacked, right? And so that means we need an additional 2 carbons. So these 2 carbons are these 2 carbons. Those got tacked on there because they attacked this carbon right there. So we just get that, hydrocarbon. We get that alkane product because of the organocuprate addition. Okay, following up on what we did before, Caitlin says, so it's still in the plane of the paper, so it's on the same face of the molecule. Okay, yeah, that kind of makes sense. So if the alkane was in, so this is planar, right? We're saying that's planar. And so the 2 groups being added add to the same face. So they either both add to this face. So I'm taking that molecule and now I'm looking at it from the side. I'm looking at the alkene from the side. They're either adding to this face or they're adding to this face. And whichever face they add to, they'll end up on that side of the molecule together. That's what syn addition is. Gib asks, sorry for my very basic questions, but when you're drawing resonance structures of more complex organic compounds, what is the process that you use to find them? I mean, there's not really a process. It's just... okay, for example, that, right? So how many resonance structures can we make, right? We can take this and we can form a pi bond here, and we can push this pi bond up onto that carbon and put the carbanion there. Or we can push this pi bond here and put this and get the carbanion there. Or we can push this pi bond here and we can push this pi bond and get the carbanion there. That would be another one. Or we can push this pi bond here and then we can push this pi bond up here and get the oxyanion. So that would be another one. So it just depends how much conjugation there is. Where are the formal charges? Which bonds can gain, or sorry, which atoms can gain a pi bond and lose, and which ones can lose a pi bond? You're just pushing pi electron density everywhere it can go, right? There are places where it can't go. For example, this methyl. There's no pi electron density that's going to get to that methyl because that methyl is not going to lose any bonds. It's not going to lose any of those carbon-hydrogen sigma bonds. That doesn't work. So there's no resonance there. But everywhere else, we had all this conjugation, all these pi bonds. So you take all the pi electrons, which are pi bonds and lone pairs, and just push them around wherever they can go. And anywhere they can stop along the way would be a valid individual resonance structure. Andrew says, how would you write out the breakdown of a hydrocarbon molecule with that of water plasma? That doesn't really sound like organic chemistry. Okay, cool. Yeah, that's all the questions. Maybe like 30 seconds if anyone's got one real quick, because we don't have time to get into the next one. But that was cool. That was a lot of questions. Thanks, guys, for all your questions. I love answering questions on the fly. I have my stuff prepared so that we have plenty to go over, but I like when we only get to do 5 or so because we have so many questions to talk about. So, yeah, that's the time. So once again, I'm coming to you live every Tuesday at 5 p.m. Pacific, partnering here with Chegg to bring you Organic Chemistry 1 office hours. And so we have a few more. We have, I don't know, 4 or 5 more of these, I believe, to round out the semester. And check out that QR code if you want to see what other courses they're offering. Chegg and I want to help you with all the courses that you're taking this semester. And tune in next Tuesday at 5 Pacific time to do